بسم الله الرحمن الرحيم والصلاة والسلام على أشرف الأنبياء والمرسلين. بسم الله الذي لا يضر مع اسمه شيء في الأرض ولا في السماء ولا في السماء. اللهم ربنا صل الله وسلم على رب اجعل في الصلاة وزكاة ربنا وربنا اغفر لي ولوالدينا صادراتك يا أرحم الراحمين. بسم الله الذي لا يضر مع اسمه شيء في الأرض ولا في السماء ولا في السماء. وصلى الله على سيدنا محمد وعلى آله وصحبه وسلم. Yes, so this morning we have been looking at heat transfer in three-dimensional coordinates. So we have looked at heat transfer in rectangular coordinates as this, cylindrical and then spherical coordinates as this. So eventually we derive the general equation for heat transfer in rectangular coordinate as this. And we came up with 1 over alpha derivative of dt over dt equals 2. We have also the square over the x squared plus the squared over the y squared plus the squared over the square, and then plus q divided by k. So this was the fundamental equation that we derived. And we define one parameter, a new parameter called alpha, is k divided by rho times c, where this is told is the thermal diffusivity. So the thermal diffusivity, by classical definition for thermal diffusivity, is that it is the ratio of the thermal energy which is transported relative to the thermal energy storage. Okay, so I'm told that whenever the thermal conductivity of a particular fluid is very high, then it means then you have the high thermal diffusivity. But on the other hand, the Cp is more related to energy storage. So we have a fluid which stores energy relative to energy transport. It means the thermal diffusivity is going to be low in this phase. Okay, so this is the general equation, and then we apply certain boundary conditions. Surface boundary condition, then constant temperature boundary condition, convection boundary condition, and so on and so forth. Okay, so we have 4 primary boundary conditions we have looked at. There is one last one, which is very important boundary condition, which is called symmetric boundary condition. This you cannot find in the lecture notes, so please, you may have to write this symmetric boundary condition. And the importance of this boundary condition is that they will enable us to solve the very big equation we have at hand. A very large equation, but we need to simplify it to a very simple form. So, symmetric boundary condition. Symmetric boundary. You can tell that it's normal fact. Boundary condition. It is like this, that if I have, let's say, 2 surfaces, okay, I have 2 surfaces, or we can take, let's say, from this, before I go to this, let's see, if I have a fluid flowing across a flat plate, okay, so there is a hot flat plate, so this is the ds, this is the temperature of the fluid. So by virtue of the heat transport across this flat plate, the temperature distribution is going to be, so you have temperature, so here we have ds is greater than T infinity. So the temperature profile is going to be like this. It means the temperature will be increasing. We have a large temperature here. The temperature will be reducing gradually, asymptotically, until eventually when you have T will be equal to T infinity. So this is the temperature distribution, temperature profile for when a fluid is flowing across a flat plate. So this is a high temperature, this is a lower temperature. In a similar fashion, if I have vertical plates, okay, and a fluid is flowing, let's say we have air flowing across these two plates, we have a symmetry like this. Symmetry means, when we say symmetry, it means we divide something into two equal parts. Whatever happens on the left is the same as what happens on the right hand side. Okay, so we divide this plane into two like this. Now we have the air moving across this plate. Okay, the temperature profile, as far as the air distribution, the distribution of the temperature is going to be something like this. Let's see, equation like this. This will be the temperature distribution. Means we'll have a high temperature here and a lower, again high temperature. Temperature will be reduced in this way. These are hot plates. The air is flowing in between them. So if you take one side, same as this. These are the high temperature reduces asymptotically in this way. The same thing, you have two plates mounted vertically upwards. The fluid is flowing in between them. So if I want to draw the temperature profile for this plate, with respect to this will be high temperature, it will be reducing, and then it will reach a constant. It's not equal to 0 over here, but it has a finite value. You understand? Similarly, also here the temperature will be reducing in this way. So that when we say symmetry boundary condition, if as far as the temperature distribution is concerned, or the heat transfer at the, can I delete this now?
Yes.
Yeah. We can say that at the, or let's say at the symmetry, the rate of change of temperature. So temperature distribution T, let's say this is our coordinate as is x, and then the middle portion, and this is x equals to 0, and this x equals to L, and this will be x equals to L divided by 2. Okay, at the point where x equals to L divided by 2 is, I have L divided by 2 and time t. The derivative of this temperature with respect to x is always equals to 0. So I will explain. Just be a little bit patient. Okay, so please bring your mind again here. Here we have a high temperature over here. What do you observe? The temperature starts reducing until it gets to the center. Similarly, the temperature will be reducing all along up to this point. But along this symmetry, is the temperature changing or not? The temperature is not changing. So that's why we say that the derivative, the rate of change of temperature at this point, at the center, the temperature remains constant. It does not change. It's not equal to 0. It remains constant. So the rate at which temperature is changing with respect to x, where x equals to L divided by 2, that equals to 0. And the application for this application can be found in a cylinder. We have a cylinder like this. Okay, and in this cylinder we have R, let's say R0, and this is R1. Okay, so we have a fluid flowing inside the cylinder. So as far as the temperature distribution is concerned, I've told you for all cylinders, temperature is a function of the radius. Temperature changes only in the radial direction. Discussed that this morning. For all cylinders, if you have a hollow cylinder where a fluid is flowing across it, temperature changes only in the radial direction. So it means that for this particular case where we have, let's draw our symmetry. This is our symmetry. So this is RO and this is R1. So this temperature is changing only along this direction. It also changes along this direction. Okay, so it means that as far as symmetry for a cylinder is concerned, so the symmetric function. So symmetric function for cylinder can be expressed as the derivative of T at R with respect to R when R equals to 0. What will be the temperature? The answer. So R equals to 0 at time T with respect to R, not the X. This temperature is a function of R. R equals to 0 means at the center, at this point. So along this direction, temperature remains the same, doesn't change. Temperature only changes in the radial direction. You can have a situation where you have let's say you can even have this to be 100 degrees Celsius. So progressively as you move outwards, the temperature will be decreasing. You can have 100 here, you can have 90 here, 80, 70, and so on like that until you move to the outer surface of the cylinder. But along this line, it will still be 100. This is 100, this is 100, along this line. But any point along this, temperature is changing. It is changing in the radial direction, but with respect to the symmetry, any point along the symmetry, the temperature is the same. So this is what we refer to as symmetric condition. It's very important, and this is equal to 0. This temperature along the radial direction or the symmetry should always be equal to 0. Okay, so with this, let us apply some of this knowledge to solving questions. Okay, so is there any questions so far? Okay, so later on, let's say when we start solving questions, maybe there will be questions will be arising out of some of you. So by now it's a little bit earlier to be asking questions. So have you written this already? Yes.